Hello everyone, I'm Chongkai Gao. Today I'm going to introduce our paper, Iterative Interactive Modeling for Noting Plastic Bags. This work is done with the cooperation of Zekun Li, Haichuan Gou, and Feng Chen. Deformable object manipulation is a long-standing problem in robotics, and there are several researchers recently that have achieved promising results with the help of advanced techniques from computer vision and robotics. However, these works still focus on traditional deformable objects such as roofs, clothes, doors, and plastic. More challenging deformable objects remain unexplored. In this work, we challenge the problem of noting plastic bags that dropped from the air. What are the challenges of this task? We point out that the challenges are from the physical properties of the plastic bags that make prevailing methods infeasible. First, the infinite initial configurations of plastic bags and the self-occlusion problem of the randomly dropped plastic bag make directly using 2D vision-based methods infeasible. This is an key point detection result in our paper that is performed at the initial configuration. We can see that the skeleton directions results are not accurate. Secondly, the transecute and non-labyrinthine surface of plastic bags make 3D vision-based methods infeasible. For example, this is a depth sensing result from a RealSense D435i camera. We can see some parts of the bag are blurry. Thirdly, the intricate and non-uniform physical properties make no simulator can be used for simulating plastic bags. And lastly, the extremely lightweight and non-quasi-static motions make it impossible to learn a dynamic model from vision or tactile sensors for the plastic bag. For example, the bag would gradually fall down with no external force. In summary, the challenges come from both representation and manipulation. So how do we tackle this problem? Our idea comes from how humans solve difficult manipulation tasks. For example, if we want to lift up a couple whose handle is on the other side, far from us, we will not directly lift it up. Instead, we will first turn it around and then lift it up. Another example is about folding clothes that is in a mess. We will first spread it out and then fold it. This example shows that to solve a complex problem, we should first transfer the initial state to a standard configuration and then accomplish it. Thus, for our plastic bag problem, we should first lift it up to a standard standing pose, then tie the knot. But is this feasible? Our answer is yes. If we can hang the handles of plastic bags to the robot arm, we could probably solve the task based on recent works. So in this work, we first shape the plastic bag to a standing pose with iterative interactive modeling. Then note it with this model and a set of learned motion primitives. Let's go through our method step by step. First, the core of IIM is a model of the plastic bag. We choose to use key point skeleton as a representation since its properties. It is sufficient to support intricate manipulation. It is more concise than dense descriptors, and it is feasible for current computer vision methods on plastic bags. The problem is there is no existing dataset for plastic bags. To this end, we propose a new dataset with 43,200 images of plastic bags from different configurations such as background and illumination, and label each picture with 19 defined key points and the bounding box. We then train a state-of-the-art 2D K-point detection model on this dataset. This shows the training results. We can see that although we have data on different configurations, the detector only performs well at the standing pose. This confirms our idea. Thus, our goal is to get the 3D K-point skeleton from the initial state. IIM first picks up a lying bag with iterative pick-place actions. We leverage spatial action maps to perform this action. At each time step, the red camera gets a top-down view image, and it is rotated and segmented to be processed by a fully connected network. The network outputs a series of heat maps where the higher value indicates higher possibilities of grasping. We select the point with the highest value with some distance constraint to get the final grasping point. Then we transfer the pixel XY coordinate to the robot configuration, and then use CoMap to get the grasping depth. Finally, we perform the grasping action based on the estimated XYZ value. But how do we train the spatial action maps? In this work, we use imitation learning to train them from human experience. Instead of using teleoperation to collect human demonstrations, we design a convenient pipeline to collect the oracles of grasping points. We let the person to click on the top-down view image and transform the XY pixel coordinate to the robot world coordination by pre-measured transformations. For each grasping action, we also collect a series of side view images from the left camera. Thus, each data point in the demonstration contains one top-down view image, a series of side view images, detected 2D key points on side view images, the grasping points on the top-down image to train the spatial action maps, and a task program state to train the next module we are going to talk about to determine if the current plastic bag is adjusted good enough for the noting process. We use graph convolutional networks to determine the adjusting actions. The side view images captured by the left camera can lead to a set of key point detections. We send them to a graph convolutional network to determine if the robot needs to perform a grasping action. A graph convolutional network is trained by the collected demonstrations mentioned above. When the graph convolutional network is determined to perform node tying, we can go to the next phase. Before node tying, we need to first lift up the plastic bag to hang it on the grippers. We first calculate the inserting directions by approximating two ring planes, and then calculate the perpendicular directions. Then we insert and lift up the plastic bag by calculating and moving to the center points. After hanging the bag on the grippers, we use two trained motion primitives to tie the node. Each motion primitive is responsible for one side of the plastic bag. The wrist camera detects the grasping point, and the robot will move to the point under collision constraints. There are also some failure cases. Two most common situations are: first, the handles overlap and interweave so that the robot fails to separate them in 10 steps. And second, one of the handle collapses too deep to be grasped from above. In summary, the core idea of this paper is to use iterative interactive modeling for challenging deformable object manipulation tasks. We also show the effectiveness of spatial action maps and graph convolutional networks on plastic bags. There are also some limitations. Firstly, the key point detector and the pick place training all depend on our custom dataset, and we assume that a plastic bag can stand still after being adjusted. Some extremely difficult initial configurations, such as the handles being pressed underneath the plastic bag, are also difficult for our method. Thanks for watching.